मैं आ गया, आप मुझे बोल कर दिए।
Bismillahirrahmanirrahim. We have the first session of our fifth day of training workshop on quantum computing and quantum information. Our speaker is uh, Dr. Sabiuddin Khan Sahab, and he did his PhD from Kansas State University in the subject of laser physics. He's a gold medalist in materials engineering from UET Lahore and nuclear engineering from PIAS, Pakistan Institute of Applied Sciences, Engineering and Applied Sciences. He's been associated with the National Institute of Laser and Optronics since 2014 as an associate professor. He has more than 35 publications with impact factor more than 100. He has very good citation of his work, which is more than 2,400. He is also co-PI of Post-Quantum Cryptography Project NUST and Petawatt Laser Project and Ion Pump uh, Indigenization Project at NILOP. So here I welcome Dr. Sabi. Thank you.
Bismillahirrahmanirrahim. So thank you for the introduction. Can you hear me clearly? I'm okay. So this is the overall layout of my talk today. I'm going to be with you for the whole day, and I've divided it into 4 parts. Uh, Actually, we have talked about quantum computers a lot during the last 4 days. And a lot of people ask this question that once we have a quantum computer, what actually we can do with that? There are some very promising things which you can demonstrate and which are not here yet, but they'll be here in future. But is there anything which we can do today? What kind of threat we have from quantum computers? So I'm going to talk about that. So there are several areas where quantum computing as of this moment have a lot of impact. One of the area is cryptography. So today I'm going to focus on cryptography. Other than that, another area very important in which a lot of impact and disruptive work is going on is financial market. So financial analysis, optimization, that is also one area which is very important. And a lot of companies are already forming internationally, a lot of startups, and they're not just state-funded companies. Now we're at the level that they're like more than 100 companies internationally which are self-sufficient, like which earn through consultancy or through various products, and they are already out there using quantum using resources of quantum computing. So but today's our focus will be on cryptography. So before moving towards post-quantum cryptography, which I will cover in the fourth lecture, I will initially just introduce you with current cryptographic algorithms, just very quick introduction, and then some modular arithmetic, some mathematics, uh, which I think you guys need to know a little bit. And then once we are prepared with all the skill set, like Dr. Madiha made my job very easy. So if she's listening, thank you, Dr. Madiha. And Dr. Sarah and Mariam, they also did very good job. So I'm going to build on that concept. But now I'm going to take some, fast acceleration. I hope you guys stay with me. Okay, and then once we have all the components, all the skills in place, then I'll briefly discuss about Shore's algorithm and what Shore algorithm can do, what kind of threat we have right now for against Shore algorithm, and then finally I'm going to talk about the mitigation. That once we know that quantum computer is going to make things very difficult, keeping secret is going to be a very difficult thing in coming years. So how can we use basic mathematics, for which some foundation stone was laid by Brigadier Razak earlier on Tuesday. I'll be talking about that, and then I'll be talking about some of the products which we have already created and which we already working on. Okay, so let's start. There were a couple of questions yesterday. I did not attend. I was busy on Wednesday, so I was not able to attend whole day for Wednesday. But other days I was there on online. So one of the question, more than one person asked that we don't have a quantum computer. So how do we access quantum computer? Okay, number one, as of this moment, we don't have a quantum computer, but my institute, National Institute of Laser and Optronics, we have ordered two quantum computers. One is about to be received, and within next 3 months, it will be operational in Pakistan. The one which is about to be received is neutral atom quantum computer with 25 qubits size, and we have placed another order for ion trap quantum computer, which will be here in Pakistan within a year. So our relevant team members at Nirop, they are working on it, and some of them are abroad right now training on that. Okay. So what I'm going to talk today is part of our collaborative project, which is post-quantum cryptography, which is funded by NUST, and Brigadier Dr. Abdul Razak is PI of that project, and I'm co-PI. So Brigadier Dr. Abdul Razak is from NUST, and I'm from National Institute of Lasers and Electronics. So he'll be assisting me in most of the talks, sir, if you have, and also if I just get off track, also please bring you back on path. So I'll start with the first cryptographic primitive, which is called hash function. Okay, so what exactly is a cryptographic hash function? I'm not going to go into the detail of how these functions work. Okay, so I'm not going into the mathematical detail. If you want to go into the mathematical detail, you have to attend Brigadier Razak's full semester course at MCS NUST. Okay, and or you can catch me also. I have most of the functions I'm going to show today will be on commercial libraries, mostly PyCryptoDome. However, for cryptographic applications, we don't use libraries, we develop our own functions. So for most of the functions I'm going to teach today, I have my own version implemented in pure Python. Okay, so cryptography is a very serious effort. So first three slides, I put hash function in here is just to tell you guys that how serious is cryptography. Cryptography for a nation is a matter of life and death. It's a matter of winning wars or losing wars. Does anybody know any war we have heard in recent or past history which was won because of cryptography? It was Second World War. Exactly, Second World War. In Second World War, Hitler was using an Enigma machine, Enigma cipher, to communicate with his generals. Okay, and a guy in Bentley Park, UK, his name was Alan Turing. Alan Turing. Just a quick raise of hand. How many people have heard about Alan Turing? Okay, so history has not been very nice with him. Like he was not very lucky to be celebrated in history like he deserved to be celebrated. The other day you saw a picture of ENIAC 1, which is the first digital computer. But before ENIAC, there was another computer which was online. It was not a purely digital computer. It was an electromechanical computer. It was set up by Alan Turing at Bentley Park to break Enigma cipher. Because this whole work was hush hush and top secret, so once the Second World War was over, all science or all documentation related with that was destroyed. So unfortunately, in history, his name did not come out very well. But he was the first one to. He was one of the first few people to have to have developed the idea of how a computer works, and he used a computer to break Enigma cipher. So whenever Hitler would send a communication to his generals, one copy of that communication would be received by Winston Churchill and President Roosevelt. And MI6 was the agency responsible for providing that information. So it was the chief of MI6 whose job was to decide if this information should go to Winston Churchill and Roosevelt or should be kept secret. Because if they respond to each and every battle, so Hitler would know that his cipher was compromised. So in some of the battles, they would make their forces lose, and in some of the battles, they would make their forces win. So it was a chief of MI6 who was the guy who was playing devil's advocate, and he was deciding that which information to be released to US and Allied forces. Okay, so another war is the Falkland Wars. There's a island, Falkland Islands in international ocean, seas of Argentina, and Argentina lose that war because Argentina was using a cipher machine provided by a company Crypto AG. And Crypto AG, until recently, very recently, it was known that this company was bought by CIA right after Second World War. Okay, so right after Second World War, it was working for BND and CIA, and later on CIA owned it. So that was one company which was providing cipher generating equipment to almost all of the world, including Pakistan, including most of the Middle Eastern countries. So from history, we can learn that cryptography is a very serious thing. It's a matter of life and death, and you have to know what you're doing. Uh, so, okay, does it work? Okay, so a hash function is a cryptographic mathematical algorithm which converts an input data of any size into fixed size string called hash or digest. And it have to be a one-way function. This means that from input to output you can go, but from output you cannot come to input. If from output you can guess what the input is, then that hash function is considered a broken function, okay, or a compromise function. Where is it used? I'm going to give some examples pretty soon. So it needs to be very fast, collision resistant, and avalanche effect is very important. What avalanche effect is, at the very small change in input leads to a very large change in output. Like even if you change just a one bit of input, so output will be drastically changed. So you can actually you cannot even predict what's happening until unless you have that function with you. So it looks like just a random set of random numbers. So very common functions are SHA, secure hash algorithm. SHA-1 is obsolete now. SHA-2 is in practice right now, is still in practice. Right now, SHA-3 is in practice. So SHA-2, how many of you are familiar with Bitcoin? Almost everybody, right? So have you ever owned some Bitcoin? A quick raise of hand. Okay, so usually when you own a Bitcoin, you use an exchange, but that is not the right way of using cryptocurrency. The right way of using cryptocurrency is to own your own, is to have your own wallet. So if you have your own wallet on your laptop, a Bitcoin wallet, you require, with a very fast internet and with a very fast computer, you need 6 months to 1 year time just to sync that wallet. Right now, the size of the blockchain is around 30 to 40 gigabyte. So you need that much size of, and that computer will be mostly busy, so you won't be able to do anything on that. Okay, so usually what we do, we use exchanges, and exchanges have that wallet working in the background. And if you look at the Bitcoin, so Bitcoin have two keys. One is public key, other is private. Public key is Bitcoin address where you receive your payments, and the private key is the key which you store in your computers, or which is stored at the exchange. You must have heard that some exchange got hacked and millions of dollars have been lost because somebody was able to predict their private keys or steal their private keys, and they've been able to. So if you have the private key, you can own that Bitcoin wallet. Okay. So how much money is sitting there over there? Anybody have any idea? Billions of dollars. So if you just break, if you're just a good mathematician, and if you can end up breaking just one wallet, you can be a billionaire within a matter of seconds. Okay. So that one uses SHA-256. So SHA-256 is very popular. If anybody is doing crypto mining, so in crypto mining, basically, if you're doing Bitcoin mining, which is usually done on ASICs, ASICs are not allowed in Pakistan, but internationally it is allowed. So if you look at an ASIC miner, you will see a lot of chips, and each chip is a SHA-256 hash chip. So you just give it input and it will calculate hash. So how much speed? Uh, one of hundreds of terahashes per second. What is a terahash? 10 to 12 calculations per second. Imagine that, right? And each chip is like hundreds of gigahashes per second. Okay, so how many people have laptops? So you want to try? Yeah, please. You want to ask a question or you have a laptop? Okay. So I already sent on Discord. I already sent Jupyter notebooks. So if you guys can access that. So first notebook is named SHA-3512 something. Okay, and I can keep going, and during the break you can try. How about that? Okay, so let me show what's going on. So I have installed PyCryptodome library, and from the library I import hashlib, and from that I'm importing this function SHA-3256, and then I define my key. This is the key, or this is the input. Okay, and then I convert this input. This is in hexes, so I convert it into bytes using this bytes dot from hex and key. So now key is converted into bytes, and this byte key is given as an input to SHA-3256, and I get a hash function. And this hash I can show hash dot hex digest, and you can see this is the hash. Same I can do with SHA-3512. So SHA-3512, same key is given as input, and this is the output. Output is I've truncated the output. Okay. So is that clear? Okay, so let me make it more clear. So same with there's a Chinese hash function also available, which is called SM3. This is a Chinese standard. In coming slides, I'm going to try to convince you not to trust USA. Okay. So I hope by the end of this talk, you will be convinced that we need to trust somebody else. Most importantly, we need to trust ourselves. We don't need to trust Chinese. We don't need to trust anybody else. We need to trust ourselves. If for military application or for national application, the algorithm which you're using for encryption should be created by you, not coming from any library. I showed you library just for the sake of teaching, but it should come from your own code. Okay, so where is that hash function is used? So hash function, if you, how many people are users of Linux? Okay, so same with Linux and Windows, same thing. Your password is saved in a file, in an encrypted file. Okay, so in Linux, these days it's almost universal standard that the password file is kept empty. /etc/password. That file is kept empty. And there's another file which is called shadow file. So your passwords are sitting in your shadow files. Okay, and this is a snapshot of one of the shadow files. And you can see here USD Mux, Light EM, these are all the users. And my user is here, one of the user is comstech. Okay, and the password for comstech is here. This is in this is password. Actually, this is not the password. This is the hash of the password. Okay, for more technical terms, this part is the salt. This is the salt. This thing, and this is the hash of the password. Okay, so I have this rubber ducky with me. These are small devices. You just insert it in your computer. One, two, three, four, five. That's it. Now your shadow file is with me. It's stolen. Okay, so there you can pass around, and there are several versions of this rubber ducky device. It comes as small as possible and as large as possible also. You just put it on a computer. One, two, three, four, five. That's it. Your shadow file. I have your shadow file now. Okay, so there are different ways of doing that. One way is that it transfers the shadow file in its own memory. Second way is it transfers it, emails it to some address online, or places it on some online drive. Okay, so once I have, using rubber ducky, once I have your shadow file, then what I'm going to do, I'm going to take this part. Okay, and then uh, so let's just see. Look, if you look at this password here, it's a $6. This, all the password are uh, the first three characters are $6. What does $6 means? So this is a table. So from this table, you can see $6 is sharp 512. Okay. If you did not harden your Linux, there's a likelihood that your password is preceded by $1, which is MD5. MD5 is a compromised hash function. So always check your shadow file if you're using Linux, that you're using $6, not $1. Okay. If you're using $1, then you need to go ask ChatGPT or DeepSeek how to switch your encryption from MD5 to SHA-351, or SHA-512. Okay. Okay. Let's move. Okay. Uh, can you open that Chrome? Okay, I'm going to show you one example of how dangerous it is to do that sort of thing. Actually, I'm going to share my computer if you don't mind. Okay, okay, so can you see my screen? Okay. So I'm going to run a utility on, so all of you are familiar with Jupyter, right? So I usually switch between lot of computers, lot of laptops, so install anything on my laptop. So uh, uh, for public things, for educational thing, I don't install on my laptop, but I use Colab. So Google Colab, which is colab.research.google.com. It have all the environment set up for you uh, for Jupyter, and you can see I can run on that. So I've installed here a package which is called Hashcat. It's right now. Everybody see that? आप चलाते हैं? Okay, Hashcat is a utility to break your password. Okay. So now uh, so what we're going to do, that the screenshot I show you from my Linux shadow. Okay, so we are going to do two type of attacks. First attack will be a dictionary attack. In this attack, if you see, I've imported a text file, most used passwords.txt. So there are various dictionaries available online on which contains your passwords. Okay, like a while ago, Facebook was hacked, and all the passwords, everybody password were on that. So that file also exists. So you can grab those files, and then you see this is an echo command. So I'm creating a file. Echo is a print command in Linux bash. So you can see I've created a file hash.txt, and you see the hash part is here now. Okay, so I've brought it here, and then next I'm going to run hashcat. So hashcat has started, and right now I'm using T4 GPU. T4 is just a very starter level GPU, not something fancy. I'm just going to show you how easy it is to crack a password if you have a shadow file. So can I have my rubber duckies back? We have those. Okay, so the cracking part has started. You can see, and it have already cracked. If you see here, so if you see here, it says status cracked. So now the password is cracked. So, and all of you can do it on your laptops also. So this was the password. This, you see, I tried to make it a very cryptic password. Exclamation mark, capital Q, at, capital W, hash, capital E, dollar, capital R. Is that an easy password? So from all definitions of a password, this is a difficult password. Okay, but turns out that dictionary file had that password already in it. So that's why it was able to crack it. Okay, are you guys with me? Okay, so now we're going to move forward, but when we have time, I'm going to ask one of you to come to me, and in my Linux, you will create a password. Uh, since we are short on time, so what we're going to do, okay, let's do it now. So what we're going to do, that password, you can write it down somewhere, uh, only lower letters and numbers and 5 characters. And I want to show you that how easy it is to crack a 5 character password with a full brute force attack. This current attack which I did was using this most used passwords file. So this was a dictionary. Okay, and it was able to crack it because this password was already there in the file. So how it was executing, it will take each password from most used passwords file, and then generate its uh, uh, 3512. Okay, and then that SHA-3512 is matched with what I gave in as my input. If the input matches, then this means that I've cracked the password. Okay, so next, what we're going to do, we're going to do brute force attack. So one of you, uh, which one of you want to come? First, all of you decide a difficult password. Or maybe during the break we can do that. You want to do it during break? Okay, let's do it during the break. Okay. So can you PowerPoint में वापस आते हैं? Okay, so I just want to make you realize that choosing password is also very important. Okay, make very long passwords. Do not create password which you can remember. Do not use dictionary words. Do not replace A's with at, S with dollar sign, one with exclamation mark, right? Don't do that. As B with six, don't do this, because hackers are sitting out there. They have all those combinations with them, and they can use it. If you have access to Hashcat, everybody have access to Hashcat. If you pay anything just to see Hashcat, no. Google Colab is free. I have free access to T4 GPU. And how about what kind of access you have on a paid GPU system? You have huge. Similarly, I have another device, which is this. This is a Raspberry Pi Zero. You guys can have a look. And this one, with this, I've installed AirCrack on it, so I can hack your Wi-Fi password with that without even connecting to your password. All I have to do is you have to connect to the Wi-Fi. Like if you connect during the handshaking process, you are showing up your hash of your password. So once I have the hash, I can use again Hashcat to crack it. And I've cracked several Wi-Fi passwords with that. Okay, so don't use your telephone number as a Wi-Fi password. Okay. Okay, now coming back to our topic of discussion, I think I've got everybody's interest. So can I sit? I have a little bit problem with my leg. Okay, so there are two types of, now we have understood what a hash function is, but other than hash, there are also other cryptographic primitives. So two very important cryptographic primitives are symmetric encryption and asymmetric encryption ciphers. Okay, so how many of you don't know what a cipher is? Thanks to media, everybody in Pakistan knows what a cipher is, right? And I've just showed you a hash. Hash can also be considered a cipher. Okay, so I'm going to show you a lot of ciphers today. So what is symmetric encryption and what is asymmetric encryption? So first, let's talk about symmetric encryption. So in symmetric encryption, let's say you're two people sitting and you want to share a secret between yourself, like a top secret document you guys want to share. So there are two ways of doing that. One way is that beforehand you guys decide on a key, and now two people have that key. Okay, so now what you do, your document is here. So you take your document, you encrypt it using a key, you generate a ciphertext, or simply cipher. And then you need that same key to decrypt that cipher into plain text again. Okay, but this has been very, very powerful. If you look in history, this has been used almost a lot of different empires. Like this is coming from prehistory. Okay, lot of people use lot of ciphers. Lot of religious books are written in ciphers also. Okay, so this is okay. But what if those two people who want to share a top secret file or who want to share a secret file have never met before? For example, you want to make an online payment. So you have never met somebody. You're buying something from Amazon, but that person you have never met. So now what should be your key? Any answers? So that would be very difficult. So for that, another type of cipher game, which is called asymmetric encryption. In asymmetric encryption, you have, instead of having one key, you have now two keys. And I'm going to explain it in more detail in coming slides. So one key is used to encrypt the cipher, but you cannot decrypt with that key. And the other key is used to decrypt the cipher, but you cannot encrypt with that. Okay. So the file with which you can encrypt, that file is called, that key is called public key. And the key with which you decrypt is called a private key. In most of the algorithms, but it is not generally true that private key and public keys can be replaced also, but not in every condition. Like for example, I've given you example of Bitcoin. In Bitcoin, you cannot replace swap private keys and public keys. Okay, but in some cases you can. Okay, so anybody not clear on that? Because we're going to talk a lot about this. Everybody clear? I'm going to show you with examples. Okay, let's move forward. So now with symmetric encryption, there are two type of ciphers. One are called block ciphers, the other are called stream ciphers. A block cipher is a cipher which encrypts your input text using blocks. Okay, like there are different examples I've given: DES, AES, two-phase, Serpent, SM4, which is a Chinese standard. And then there are some ciphers which are called stream ciphers. Stream ciphers are usually used in communication, and block ciphers are usually used to encrypt document. Okay, I'm not going to talk about stream ciphers today because of lack of time, but I'm going to focus on block ciphers. So the first block cipher which came into standardization was DES, Data Encryption Standard. It was initially its name was Lucifer. It was created by an engineer, Horst Feistel, at IBM in 1971. Okay, and he applied it to be standardized in 1976 to then National Bureau of Standards, which is now uh, which is now part of NIST, National Institute of Standards and Technology. This is with USA, and NSA modified it in 1976, and they standardized it into a document which we now call FIPS 46. This was in 1977. Okay, and then there are several revisions of that. The most recent revision was FIPS 46-3, in which DES was replaced by 3DES. Okay, so the problem was that NSA, when they took this Lucifer cipher into standardization, at that time, NSA and IBM already knew that this cipher is broken, this cipher is compromised. But they still ended up getting it standardized and making it a standard for handling top secret and secret documents in USA and rest of the world. Why is that? Because NSA wanted to have access to all of those secret documents themselves. Okay, and this was later revealed after many years that this is compromised. So this is an example. Again, let me show you. So here again, PyCryptoDome library I have already installed. So previously I was using hash, but now I'm using crypto.cipher, and I'm importing DES function from there. And then this is my key 1 2 3 4 5 6 7 8, and then des.new key and mode. What is the mode? I'm going to talk about in coming slides. Okay. And then I give a message. Here I'm using a random number generator to generate a random 8-byte message. And then this is the message I'm printing. And then I am encrypt this message into a cipher. So you can see this was the message, and this was the key, and this was the ciphertext, and this was again decrypted too. So I decrypt it here. Okay, so very simple. You're just using a library. You're not making your own. Even though I do recommend you make your own. You can find a lot of open source implementation of that. And in fact, you don't need to look for implementation. If you're a good programmer, just go to FIPS-46 document. And in that, step by step in pseudocode, they have given the entire algorithm. You just need to convert that pseudocode into Python or C or Rust or whichever language you're using. Okay. So in 1999, Distributed.net and Electronic Frontiers Foundation collaborated publicly to break DES in 22 hours and 15 minutes using 100,000 computers connected over internet, just to demonstrate, because the information was leaked that NSA and IBM are privy to DES being compromised. So, again, so to circumvent that, NIST introduced the newer standard, which is 3DS in 1999 by publishing a document FIPS 46-3. And then there are other attempts also. People have used FPGA, people have used GPUs, and if you use the hashcat, you can break it very easily using brute force attack on T4 GPU, which is one of the crappiest GPU out there. Then in 1997, NIST again they brought together all the top cryptographers from around the world, especially in USA and from Europe. And they started discussing that since DES is compromised, we need to come up with another standard. That new standard, they decided to name it AES, Advanced Encryption Standard. DES was Data Encryption Standard. So this is a very long process. Uh, During the next 9 months, these were the shortlisted algorithms, and you can see Ringile here, Serpent, and Two Fish here. And then there've been a lot of discussion, and then eventually in August 99, they came up with these 1, 2, 3, 4, 5 ciphers, which were considered safe, which cryptographers were not able to break by that time. However, in coming months, uh, they took some scoring, and they saw that Rendile has 86 positive and 10 negatives. Serpent have 59 positive, 7 negative, Two Fish 31, and RC6 and Mars were rejected. And then eventually from these three, Ringile, Serpent, and Two Fish, in 2nd October 2000, Ringile came as a winner, and today you know Ringile as AES. Okay. However, at that time it was realized that Ringile was not the winner because it was the most secure cipher out there. No, in fact, Two Fish and Serpent were equally better, but in some cases, Serpent was even more stronger than Ringile. But Ringile was selected because it was able to run on everything. What do you mean by everything? Uh, in those days, mobile phones were those dummy phones, which I usually carry. So those dummy phones have a SIM card. So SIM card is a processor itself. So the condition set by NIST or NIST cryptographers was that it should be able to run on the microprocessor of the SIM card, not on the processor of your cell phone, on the SIM card. Okay, so this is a very stringent condition. So, however, today we have a lot of good processors, lot of good cell phones, lot of good computers. So today, even though AES is the standard, but Serpent and Two Fish are equally, or in some cases, even better than Ringile. However, Ringile, Two Fish, and Serpent, these three ciphers are considered quantum safe today. I'm referring back to Dr. Sara's talk on Grover's algorithm. In Grover's algorithm, you bring the number of permutations to half, but still that period is very long. Like if you're breaking a cipher in like using brute force attack, if I'm breaking it in like 30 years, so if I bring it to half, like 15 years, still it's a long period. Okay, so this is what quantum computer has impact on breaking block ciphers, that it can break in half period. Okay, but this is not good enough. Okay, so for all practical purposes, these are considered quantum resistant. So this is implementation of AES. Again, everything same as previous code. I just replace the DES with AES, and everything same. And this is the message. This is the key, this is the ciphertext, and this is the decrypted. You can see message and decrypted message are same. Okay, and you can, during break, you can try that. Okay, there have but the success of AES is its own enemy, because uh, nobody wants to spend too much time for their files to be encrypted or decrypted. So everybody wants that in a jiffy you can encrypt or decrypt, and that is a problem, because in order to make them sped up, you create special arrangement in hardware. For example, in Intel Core and in Amazon AMD's Ryzen processors, you have AES.NI instruction set, which is specially there. This is a hard coded hardware on your microprocessor just to handle AES, just to make it execute faster. Similarly, hardware AES modules are available in ARM RISC processors, and then in FPGA also there are several softwares available to brute force or to crack AES. and then similarly dedicated ASIC chips already exist, and then on GPU, both in CUDA and in OpenCL programming environments or in programming language libraries, there is special instruction set to speed up AES encryption or decryption. So now, if you can speed up AES encryption and decryption, what's the disadvantage? Now you can do a brute force attack even more efficiently. So the faster a cipher is, the more prone it is to a brute force attack. So AES is its own enemy. So, but on the other hand, Serpent and Twofish have remained mostly neglected by the microchip industry. So it is not implemented very nicely on the hardware. So if you want to do a good cipher, you have to make something in between AES, Twofish, and Serpent. Don't rely on AES. By the way, Brigadier Razak and we use quadruple encryption ciphers. Like we encrypt same message first with AES, then Serpent, then Twofish, and then Chacha 20 poly 1305. So you can do quadruple cascaded encryption to make your cipher more strong. Okay, so when we were looking at the code, there was something, a mode of a, sir, what is the time?
21.
Huh?
1221.
1221. Okay, so there are modes of block ciphers. What is the meaning of mode? So we were using this mode, electron ECB mode, which is abbreviated electronic code book. But this is not the only mode. There are other better modes also, like CBC, CFP, OFP, CTR. And then on the authentic encryption in advanced mode side, we have OCB, CCM, GCM, CWC, EAX, and then GCM SIV. These are various different modes. So I'm going to give you a very quick intro what a mode is and why we need to know about mode. So this is the original image. This is our founder, Qaid-e-Azam. And then when I encrypt this image with AES ECB mode, you can still see that in this image there is some kind of picture of Qaid-e-Azam. Okay. And this particular thing is called ECB leak. Okay. And this is because what I've done is that I've taken, this is a very big image. So I've broken it into various blocks, and then each block I've encrypted it. So what ECB is doing, that I have my encryption function here. So I've broken my image into small blocks. This is one block, this second block, this third. So this in AES, this is like 32 byte block set or 16 byte, 32 byte. So each block is 32 byte for AES 256. And then you can see for each block, I'm using the same key. So same key is used to encrypt that block of plain text into a block of ciphertext. And then I combine all those ciphertext into a single file. And this file, I say, this is an encrypted file. Okay. But because of what's the advantage of that? I can do encryption in parallel. I can do decryption in parallel because I can pick up one block and decrypt it or encrypt it. So this makes things very fast to execute on the hardware. And I can do random access also. I can just like access block number 1001 and I can access that. And I can change that block and put it back into my ciphertext. So this is very good. However, because of mathematics, you can see that ECB does not work very well in some of the cases. Not in all of the cases, in some of the cases. And this particular thing is called ECB leak. So to circumvent it, again, this is decryption. So we take ciphertext and then use decryption function and then you get plain text. So for each of the block, we do same thing, but there's only one key. Okay, and that's a problem. So now, if you so the next better block is called cipher block chaining. In cipher block chaining, we use a little bit of mathematics trick. What we do, we start with a plain text, and then we exclusive OR with an other variable. This variable I call initialization vector. I can call it anything, but in cryptography, This is a convention to call it initialization vector. And now after doing exclusive OR, I end up with a different, a more encrypted version of that. And then with that, I pass it through my encryption function using same key. And then when I get ciphertext, now this ciphertext is then goes into the next one, and it exclusive OR with the next block of plain text. Okay, so this way it is connected. So ciphertext from one block is used as to exclusive OR with the plain text of the next block, and this keeps on happening until the last block. Now this is very good, but the disadvantage here is that encryption needs to be serialized. I have to encrypt all the blocks before encrypting the last block. You understand my point? So now speed is gone. So now parallelization is gone. So I cannot run it on a GPU or run it on a multi-threaded CPU. So that's the problem here. So then they introduce another. So this is, by the way, CBC. So everything same except for mode. I Instead of mode, I'm using mode CBC instead of ECB. And then you can see here, I have introduced a variable initialization vector, which is a 16 random byte. Okay, this is all good, but then somebody came up with another idea, which is called cipher feedback. In cipher feedback, what the mechanism is slightly different. So again, instead of encrypting plain text, now what we're doing, we are encrypting initialization vector with the key. And then we exclusive OR with plain text, and then we get ciphertext, and then we keep repeating. Again, this is again serialized, so it cannot run in parallel. And then very interesting part here is that for decryption, I do not need to use decryption function. I just need encryption function of ECB mode, and I can use it in cipher block, cipher feedback, CFP mode. Okay. So this is implemented everything same except for the mode. Okay, and initialization vector is here. So this is good, but then if I want to make it parallel? If I want to make it parallel, then I have to there's a new algorithm introduced, which is called counter mode. And in counter mode or CTR mode, what I do instead of initialization vector, I use a nonce. So I use a nonce and then a counter. So first part of my initialization vector is nonce, and second part is a counter. So for the first block, the counter is 0, then 1, 2, 3, and then keeps on. And the nonce is repeated. Okay, and what's the advantage of that? Because by doing that, instead of, I don't need to go into the algorithmic detail of this, but the advantage is that I can end up doing it in parallel. Okay, this is encryption, this is decryption. Again, you can see that both encryption and decryption, you're using encryption function. You're not using decryption function. So encryption function is the only thing you need in that. Okay, and this is implementation. So the only thing is the change is instead of initialization vector, I'm using nonce, and I'm using import in giving nonce as an input here. And then I'm using CTR mode. Okay, this is one of the most secure modes, but there are other things in play which I don't have scope today to discuss. So that's why I recommend all of you to use AES GCM mode. This is not the most secure mode, but relatively little bit more secure. Okay. I do recommend people using CTR mode. For simple file encryption, CTR mode is very good, but for communication, for AEAD, AES GCM is best. And it have all the goodies of CTR mode or ECD, and but with extra security. Okay, and then there is a Chinese cipher also, which is called SM4, and you can see SM4 exactly same that SM4 dot encrypt, and again you have to tell it mode. So it also have mode CBC, ECB, CTR, GCM. All those modes also exist here. In fact, Chinese block cipher SM4 is kind of mathematically kind of copy of AES. Not exactly, not ditto, that if something is encrypted with AES, you cannot decrypt it with SM4, or something encrypted with SM4, you cannot decrypt. But mathematically, it's very similar, similar structure. And security wise also similar. So what about quantum attack? I already told you that with Grover, you can reduce the number of permutations to half. So instead of for AES 256, instead of 2 raised per 256 permutation, now I have to do 2 raised per 128 permutation, which is still long enough. So for all the practical purposes, it is internationally established that AES or block ciphers are considered quantum resistant if you're using AES 256 or better. If you're using AES 128 or 192, then they are not quantum resistant. So this is decided internationally that again through a lot of calculations, a lot of computations, that AES 256 is quantum resistant. Okay, everybody with me? And these are some of the recent attacks, some of the recent papers over attack on AES. You can have a see. So I've shared the slideshow so you can look at these papers. Some very nice papers. So now I go to asymmetric encryption. Okay, so in asymmetric, as I already told you that we need two keys. One is public key, one is private key. So the first asymmetric cipher was invented by Rives, Shamil, Adam. It's called RSA. So these three guys, Ron Rives, Eddie Shamir, and Leonard Adam, these guys were sitting in MIT, and they kept working for over a year. That what if two people have never met together? So then how would they exchange the key? Okay, so by the way, this is 1977. So this was the making, the work they did in 1977 is the reason why we are using internet today. Why we are doing electronic transactions on internet. Otherwise, if asymmetric cipher would not have been invented, then we would not have been able to do that. Okay, and then during a Jewish holiday in April 1977, Alderman was Rivest, Shamir Rivest was Jew. So Shamir Rivest was very frustrated that they were not able to figure out a mathematical algorithm. So the legend has it that he stayed up all night, kept drinking, and he kept reading big, very fat mathematics books. And by the time when he woke up in the morning, he had already invented. This is what Shamir Elderman, Shamir, Eddie Shamir later told. I don't know if it's true or false. But anyway, by the daytime, he was able to invent. And they patented it in 1983. So RSA has been doing very good until recently. So let me give you an example how RSA works. RSA is based on modular arithmetic. I'm going to focus on modular arithmetic in the second lecture. Okay. So let's say I start with two prime numbers, P and Q. In this particular case, I'm using 59 and 73. Okay. And then I multiply them to get a number N, which is 4307. Now I do P minus 1 multiply by Q minus 1. Okay, and I get another number which is 4176. This 4176 is called quotient function. Okay, now, okay, since we are doing a communication thing here, so let's call these people. So this guy I'm going to call A for Alice. Okay, and this one I'm going to B for Bob. Okay, and then there's a third guy, which is the evil guy, E for evil, or it's eavesdropper. What's the Why is there noise in the mic? What? Guys. Okay. So we're going to call sender. We're going to call Alice, and receiver. We're going to call Bob. We thought about Muslim names also, right? Sir? Do you remember the Muslim names? We forgot. One time we thought about Muslim names also, A and B and E. Anyway, so now what we're going to do that Alice is going to select a number E, which is between 1 and totient function. Let's say Alice picks 1501. Okay, and then Bob, what we'll do is for Bob, we use this function e raised power minus 1 mod totient function, which we end up getting 3397. By the way, this is not e minus 1, this is e raised to the power minus 1. Okay, so now the public key is e and n, and private key is d and n. Okay, so this is all of these calculations are being done by Alice. So Alice created these keys, and we call this process is called key generation. Okay, so now we have public key and private key. Now Alice sends the public key to Bob, and Bob, using that public key, is going to send a message to Alice, which Alice can decrypt with a private key. Okay, let's see how it works. So let's say Bob wants to send 98 as a message. So Bob sends 98. What Alice do? She do this. M raised per E. M is your message. E is the number coming from your public key. M raised per E mod N. Okay, and you end up getting 1235. 1235 is your ciphertext. And when Alice receives 1235, so what Alice will do, 1235 is C. So C raised per D mod N, and you end up getting 98, which is the same number. Okay, you understand that? Everybody clear on that? So again, the notebook I have given, there is exercise in that, so you can do these calculations over there. And you're going to, since modular function is used here, so I'm going to explain modular arithmetic in the next lecture. So this is called public key encryption, PKE. First step, key generation, which we also call key gen. Second step, encryption, in which we take a message and a public key and we generate a ciphertext. And step 3 is we take ciphertext and private key and get a message back. Okay, so key gen, encrypt, decrypt. Very simple, right? Can I use it for other things also? I can do digital signature. What is digital signature? Like, we are old people, old school people, we do signature on paper. Okay, but now these days in your cell phones, you have your digital signatures in your cell phone. So how does a digital signature works? So what happens that public key, in this particular case, public key and private key are interchangeable. This means that with your private key, you can also encrypt something, and with your public key, you can decrypt it. Okay, so what I'm going to do, I'm going to, okay, if I want to create my own signature, so I take my name, Sabiuddin, and I take it as a message, and then with my private key, I'm going to encrypt it, or I'm going to sign it. So first step is same as before, key gen. I have public key and private key generated exactly like I showed you with those calculations. And then I take my name and use my private key to sign, and I get a cipher which now I call my digital signature. And this digital signature, anybody can verify. How they can verify? They can take my digital signature and decrypt it with my public key. And this step, instead of decryption, we are calling verification. And you get my name back. So if you get my name back, this means that this is, if somebody else have signed my name. Okay, he does not have access to my private key, so he would have done it with some other key. So when you try to decrypt with my public key, you will not get my name, you will get some gibberish. Okay, and this is very simple technique, very powerful, and it's being used everywhere, especially in Bitcoin or in modern banking things. Almost all the messages you send on internet has especially secure messages like TLS or secure socket layer. You guys use website HTTPS, hypertext transfer protocol secure. S means secure socket layer, SSL. So SSL implement this methodology. So there's a third variant, which is very powerful variant, which is backbone of internet right now, backbone of mobile computers right now, which is called key encapsulation mechanism. Everybody understood DSA and PKE? Okay. So now I'm going to, this is little bit more difficult, but not very difficult. So again, step one, EGEN, public private key. And then in second step, we have two parts, encap and decap, encapsulation and decapsulation. So what I do, I take my private key and a random number, and then I encapsulate. So I get a cipher key. That random number is my key. Okay, so now I get a cipher key, and then the random number I selected, which I encrypted as cipher key, I'm going to use it to encrypt the message using a symmetric cipher like AES. So now this is a hybrid thing. RSA is used on encapsulation decapsulation side, and AES or Serpent or Twofish or SM4 are used on the symmetric cipher side. And then to decrypt it, now what you send to the receiver, you send two things, cipher key and cipher text. So from cipher key, using your public key, you get your key, which is same as the one used here. And then using that key and the cipher text and using symmetric decryption, you get your message. Okay, this is key encapsulation mechanism, and KEM or key encapsulation mechanism is backbone of all modern communication over internet or mobile telephone. Okay, without it, internet would not work. Without it, your credit card transaction would not work. Okay, do you guys understand that? Only terminology, same as encryption and decryption, but we just named it encap and decap. Okay, nothing very complicated. If it is, please ask me. Okay, let's move forward. So this is an example of RSA using KEM. So here I generate keys. So this is my private key and this is my public key. Okay, and this is my message, which is a random number. And then I encrypt it using this function, PKS, PKS1, PKCS1, this OEP. This weird name comes from NIST standardization. And I gave it my public key, and then I encrypt the cipher and I get ciphertext. And this ciphertext is decrypted back. And so this was my plain text, and this is my decrypted plain text, same. And behind the scene, these two functions, RSA and PKCS1-OAEP, they're using KEM, which I demonstrated in the previous slide here. Okay. So no need to do any programming. You can just use this library. Like 99% of the people internationally all over the world use these libraries. However, this is just 1% whose job is to keep top secret documents safe. They don't use these libraries. They develop their own. Okay. Next is Diffie-Hellman. Diffie-Hellman, this was paper published by Whitfield Diffie and Martin Hellman in 1976. And they gave a very, again, this is a very simple mathematics, but very elegant. Okay, let me explain. Again, modular arithmetic in play. So what they do, they pick two numbers. One is P, which is a prime number, and this everything else we're going to do is going to be a modulus of that, which we call primitive root of that. So G is picked as one of the primitive. So I'm going to give you example if I have a screenshot. No, okay, but I have one of the example worked out. Sorry. Yeah, no. Okay. Anyway, I have in the Jupyter notebook, I have worked out an example similar to that. So I've written some code, and you can calculate primitive roots of P. So again, let me repeat. P is a prime number, and then G I select as one of the so P have several primitive roots going to pure mathematics, which Brigadier Razak tried to explain the other day. And then I can, I'm free to pick any one number from those primitive roots. So I pick 5 in this case. Now I start with that. So now Alice can choose a number. So in this particular case, Alice chooses A. And then Alice calculates capital A, which is G raised by A mod P. And this new number, which is capital A, Alice sends it to Bob. Okay, so on the communication side, A is not communicated, capital A is communicated. Similarly, Bob chooses another number. In this particular case, Bob chooses 3. By the way, here A and capital A in this particular case are both equal to 4. This is just by sheer luck. Okay, but usually A and capital A are different typically. And then Bob chooses another number, B, and then he calculates capital B using G raised per B mod B. And this new number is 10. And Bob sends that capital B back to Alice. So now Alice have small a and capital B, and Bob have capital A and small b. So now, and this is where the beauty of mathematics comes in. So Alice calculates a shared secret, which is S, which is B raised by A mod P. And this number comes out in this case to be 18. But when Bob calculates A raised by B mod P, he also gets 18. So this is where beauty of mathematics is, that they have two different numbers, but these numbers are somehow related by modular arithmetic, and both of these end up calculating shared secret, which is 18. So now you have same shared secret on both sides. So now you can use that to encrypt all your communication. Okay, now in this table, I'm going to show that what Alice have and what Bob have, what Alice does not have and what Bob does not have, and what Eve does not have. So in the start, when they decided about P and G, both Alice, Bob, and Eve, all three have that because they communicated. Eve is listening to the communication channel. So all three have that number. But then when Alice picked A, Bob did not have A, and Eve also did not have A. Okay, so when Bob picked B, Alice did not have B, and Eve did. So Eve neither have A nor B, but Eve have capital A and capital B. So since Eve does not have small a and small b, so Eve cannot do this calculation. S is equal to A raised per B mod B, or S equal to B raised per A mod B. So Eve is unable to do this. That's why Alice and Bob can share a secret, but Eve cannot. Okay. Similarly, there's a third type of asymmetric cipher which is called elliptic curve cryptography. I'm not going to go into details of that, but Neil Koblitz and Victor Miller in 1985 invented that. And this is also very, and this is not just one elliptic curve. There are a lot of elliptic curves, and some of those elliptic curves have been selected to be used as encryption cipher. So this came into standardization in 1999 by NIST, and they have picked 15 elliptic curves for digital signature algorithm. Okay, and this has been used everywhere. TLS, SSL, everywhere. And lot of people suspect that NSA have backdoored it. This is not I'm saying. This is a lot of publications, lot of cryptographers. Okay, and then Chinese also have alternate of ECC, which is called SM2. So ECC implementation is little bit more complicated in PyCryptodome. So instead of doing that, I'm going to show you how ECC works in Chinese. And you can see here, I'm doing keygen. Chinese alternate is called SM2. And then here is my message, which is a random number. And then I create cipher key with that message. In this case, this message is my key. And then again, I can decrypt it. So this is my shared secret key, public key. This is my message, and this is my decrypted message. So in this case, if Alice and Bob can share a secret, which is same on both sides. Getting boring? So I'm coming to end. Is a quantum attack possible on RSA? Yes, it is possible because how to do an attack on RSA? There are various type of attacks, cryptographic attacks on RSA. One of the attack is called factorization attack, which I'm going to discuss now. So in factorization attack, what they do, the task is that public key is known to everybody. Okay, so can you predict from public key, can you calculate the private key? Like in case of Bitcoin, your public key is your Bitcoin address. Okay, so if somebody can get private key from that, he can own all of my money. Okay, similarly, if you go on dark web, Tor, so Tor picks exit node, entry node, and then lot of onion nodes. Okay, so all those nodes have their public keys already saved in an international database. So you have those public keys. So if I can get private keys from there, I can own the Tor network also. Okay. So public key is E and N, remember? So N is P multiplied by Q. But I don't know P and Q because if I would have known P and Q, then I would be able to do P minus 1 multiply Q minus, I would be able to calculate torsion function. And if I have torsion function, then using this, I can get D. E raised power minus 1 mod pi. Pi is my torsion function. Okay. So the only reason I'm not able to get D, because if I have D, my private key is D comma N. Okay. So N I already have in my public key, but D I don't have. So I'm not able to do it because I don't have torsion function with me. Because torsion function is P minus Q, P minus 1, Q minus 1. Because I have N, but I don't have P and Q. So if I can factorize N into P and Q, I will be able to do it. This I'm going to teach you after namaz break, which we call Shor algorithm. Okay. So before going to Shor algorithm, I already told you that what can be done with why Shor algorithm, why you want to study that algorithm at all. So can a similar quantum attack is possible on Diffie-Hellman? Yes, of course it is. Diffie-Hellman, the security of RSA is based on factorization. However, security of Diffie-Hellman and elliptic curve cryptography is based on discrete log problem. What exactly is discrete log problem? Okay, so discrete log problem is as follows. So remember something raised by something mod p. This is what I was doing in Diffie-Hellman. So I want to, end of the day, I want to solve this equation. G raised by x equal to y mod p. I want to solve this. If I can solve this equation, then I can own the network. P again is like previously I was using 23. So P is that number. And G is my generator. Previously I used, I think, 5, which is one of the primitive roots of P. Okay, and P and G are usually known. Y is a value which is known, but I want to get value of X in this equation. So if I take log then I end up getting this problem. X log to base G, Y and mod B. And this problem is called discrete log problem. If I can do this, then I would be equivalent, because since Eve have capital A and capital B, so with this problem, Eve can get this X, which is small a, or Eve can get small b. So this is called discrete log problem. So for if Eve wants to get A, we would be using this equation. If want to use B, Eve would be using this equation. Okay, so this is called discrete log problem. Turns out Shor algorithm can be modified to do a discrete log problem. So this is called Shor DLP. I'm not going to teach you a Shor DLP. This is little bit more complex than, like, teaching Shor is already a very difficult task, which I'm going to handle after the mass break. But teaching discrete how to use Shor to do DLP is even more complex thing. So I'm not going to touch it today, but I'm going to show some of the results which I'm doing on my system. So IFP is 23, G is 5, A is 4, and small a I've been able to get equal to 4. Okay, so I'm using Cascade and my own implementation of Shor algorithm, because Shor algorithm is not there in Cascade algorithms anymore. So Shor has been depreciated. Okay, so because Shor is depreciated, so you cannot use the Shor function. So you have to make your own programming to do Shor, which I'm going to explain in lectures. Okay, so ECC can be broken, in fact, more easily. Why I'm focusing on all these things? Because you're just learning this for the first time, but very, very learned people end up making mistakes. MasterCard, how many of you are familiar with MasterCard? It's an international company, right? Visa and MasterCard, two rival companies. So a couple of years back, MasterCard hired quantum mechanics experts to suggest them that how to come up with a different algorithm which will be secure against attack from quantum computers. So you know what they did? They ended up suggesting to MasterCard that instead of using RSA, you use ECC. But there's a lack of knowledge here. Why? Because in if you look at the equivalent security bits of an algorithm, so for 192-bit algorithm, RSA size is okay. So let's talk about 112. So 112 algorithm, RSA, you use RSA 4098. This is already pretty strong. But for ECC, you use this. Sorry. So 112-bit RSA or 112-bit equivalent ECC, to break that, you need 4098 qubits to in short to break RSA. But to ECC, you need 2042. So imagine if I would be in MasterCard, I would have, fired those consultants. So even very learned people are not very clear about the mathematics. If you want to learn that mathematics, Brigadier Razak is sitting here. Okay, you need to take his course next semester. So next semester, maybe. So he teaches every one year. He teach one semester this course. Okay, so you need to enroll. So that's it for now. So next lecture we do now or after the mass? Master work. Next you will do it. Yeah, this is the second lecture, modular arithmetic, then Shor, and then learning with others. Okay, we can, sir, just 5 minutes I can finish. Okay. Okay, so modular arithmetic is based on a function which is called modulo function. This was invented by Carl Friedrich Gauss in 18,001 in a Latin book. This is the cover, just to, brag that I have that book with me. It's in Latin, I cannot read it, but I have that book. Okay, so what does the modular function do? Let's come to the get to the chase. So if I have a number a, okay, I can write it as a is equal to n times q plus r. And every number can be written like this: n times q plus r. R is the remainder, q is the quotient. Okay, and n is the number with which you want to divide it by. Okay, so everybody clear about that? Any integer can be written like this. Okay, and now I have two functions. One is modular function, which is a percentage n. So a percentage n gives me r. Okay, and I have another function which is a double slash n, which is integer division. So I'm going to give some examples. And then if I have that, then I end up creating a function which is this: a what a is congruent to r mod n, where a is n times q plus r. So this congruent notation does not have q in it. Okay, why it doesn't have q? Because to introduce q, I have to do lot of divisions, and actually I want to use modular arithmetic to avoid those divisions. Okay, I want to why we are using modular arithmetic, because we want to multiply, divide, or add very large numbers without using a calculator, or very large the numbers which are right now used in RSA or Diffie-Hellman ECC are very huge numbers, so a calculator cannot calculate those numbers. Okay, I'm going to give you examples. So where's my bag? I have a calculator in there. So anybody who's fast at doing calculations in a Casio calculator? You volunteer? Okay. So you're going to do these calculations on behalf of everybody. You can sit over there, but you need to do these calculations. Okay. So now let me give you an example. For example, I want to do this. I want to add two numbers, a plus b, and then multiply it by c. Okay. So what I can do, I can split a into modular congruent form, b into congruent form, and c into congruent form. Can you do that with a calculator? So if my a is 17, b is 9, c is 4, and n is 5. So what you do, you divide 17 by 5. You end up something 3 point something something something. So, but for integer division, you just take the integer. So now your n is 3, right, sir? And then you do so next what you do is that from 17 you subtract 15, and you end up with a remainder of 2. So here I have it. So I have 3, 2. This is n. Okay. So in modular form, I can write 17 congruent to mod 5. And I can do same for all three numbers. And then modular arithmetic can be done in two ways. In fact, it can be done in three ways, but I'm going to tell only two ways. First way is that apply modulo in the end. Do all the addition and multiplication yourself, and then do modulo in the end. But this is not very helpful. But second way is that you apply modulo at each step. So what we do, instead of multiplying these numbers, adding a plus b and c, what we do, we transfer it into a modular form. In modular form, a plus b c congruent is r1 plus r2 multiplied by r3. And turns out this is easier to do. Why this is easier to do? In the next slide. So suppose I have a bigger number. So now we cannot do it in our head. Okay, so one number is this 987654. The other one number is 123456. And then the third number is 789. And I want n is 5 here. Okay, so I want to see that if a plus b for some multiply by c for some reason is divisible by n by 5. So why I want this information? I need such information in cryptography. So you can end up doing that. So by the way, if I convert it into modular form, you can see the modular form. So I don't need to get this q thing. Q thing is pretty big. So I can just figure out what the remainder is, and I already know. So this a, this is remainder, and this is this. So this is, I can figure out just by doing mathematics in my head. So that is the advantage of modular arithmetic. Imagine working with these numbers. Can you try these numbers on your calculator now? Can you add a plus b and then multiply it by c? So you won't be able to do it on your calculator. But once now you're adding a and b, right? But when you multiply it by c and then try to divide it by 5, you will end up getting an error, right? Because it's beyond the limit of your calculator. But I can do it in my head because you see, I'm using n equal to 5. So I'm doing mod 5 thing. Mod 5 thing means that I need to figure out a number which is divisible by 5. Okay. So A is this whole big thing, and in the end, I have 21. So if I take 1, I get 20. 20 is divisible by 5. Okay. So this means my remainder is 1 here. Right, sir? If I'm doing wrong, please correct me because I'm a student in this thing. Okay. And again, in this big number, if I have last two digits are 89. So if I take 4, if I subtract 4 from this, I end up with 85. 85 is divisible by 5. So my remainder is 4. So now I have only this information, 1 mod 5 and 4 mod 5. Okay, and again for this third number c 9999, again I can see from last two numbers is 99. So I take 4 off, I get 95, which is divisible 5. So I have these numbers 1, 4, and 5. 4 and 4. So I just multiply 1 plus 4, multiply by 4. I end up getting answer. You see, so this is the power of modern arithmetic. We can work with very large numbers without actually using a calculator. Just simple, you can do it in your head. So these are some of the properties of modular arithmetic. If these are really, really crazy properties. So you have to do mathematics with your own hand, or you just have to memorize them. Because the first time I read those, my head was spinning when I did Chinese remainder theorem. Literally, my head was spinning because I'm an engineer. I'm not a physicist by first degree. I learned physics in during my PhD. So I took all the courses, but I took all the graduate level courses. Undergrad course, I think I took like applied quantum and classical mechanics. Those are the only two courses I took, undergrad ones. So the mathematics was daring for me. Okay. Anyway, so these are some of the properties. I'm not going to go over these properties. And just by the way, our brain is hardwired. Modular arithmetic is not something we are not familiar with. Our brain is hardwired to mod 12, and mod 5 and mod 10 is also very easy. Mod 2, in fact, is also very easy. Okay, but by default, when we are growing up, when we are like 4 or 5 year old, our parents teach us mod 12, which is clock, 24-hour number system, 12-hour number system. Okay, so this is modular 12. Okay, and this is modular 89. Modular 89, I'm going to talk about my last talk. Just for the sake of completion, the mod thing which I told you is not a complete picture. In fact, this mod function have a subscript associated with that. So the mod function I told you, the modulo function I told you, this is modulo with offset of 0. But in advanced mathematics book, you can end up seeing a mod with a subscript of a number which we call d, an offset. We don't need to go into the detailed discussion of that because it's not relevant here. But like I taught you modular arithmetic, and then you end up seeing this notation. You say, "Oh, so we taught us wrong." So it's just for the sake of completion. Okay, I'm done. So we have done.
So we should be back at 2:30. So think we have stop break, then talk is done, and we shall be coming back at 2:30. Thank you. Thank you.
Any best? Okay, so now we are going to talk about Shor algorithm. Okay, it's really very difficult to teach a Shor algorithm to an audience who's just introduced to quantum computing like a couple of days ago. So for many years at NILOP, we struggled how to teach Shor algorithm in such a way that you end up learning something out of it. Because usually when you learn it, you learn it for the moment, and then later on you forget. And what comes in your mind that this is a very difficult algorithm, which I will never use in my life because I've never understood it. Okay, so I ended up watching this video from Veritasium. Veritasium is a very, very nice vlogs. There's a guy on YouTube. He have a channel with the name Veritasium, and he make very, very good vlogs. Just a quick raise of hand. Anybody have ever heard of Veritasium? Okay, I'm a big fan. That guy, I don't know if he's a physics graduate or not, but he usually put lot of effort in his. So I learned this style of teaching Shor from there. So I'm going to do an experiment with you guys. Let's see how it. So suppose we want to factorize a number 77. Remember when we studied RSA, what we wanted to do is we have a number n and we want to find its two prime factors p and q. So if I can find p and q, then I can calculate p minus 1 and q minus 1. I can calculate totient function, and from totient function and the public key, I can calculate the private key. Okay. So in this case, 77 is composed of two prime factors, 7 and 11. Okay. However, this is a small number, but usually the numbers are very large. So I'm going to give an example of a small number, and then with that example, we're going to scale it up to a larger number. So to do this, what I'm going to do, I'm going to select another number, which I'm going to call G. Just any number smaller than n. Okay. So maybe whatever number you can try with different numbers, but with each, I'm going to show you that with each choice of the number you'll always get a very similar result, what that result is. Okay, so I take G, and then R is my serial number here, 0 1 2 3 4 5 6, and then I take G raised per hour R. So G was 8. So 8 raised per 0 is 1. 8 raised per 1 is 8, 64, 512, 4096, and so on. Okay. And then in the next table, I'm going to write G raised per R divided by N. And integer part I'm going to write here, and the remainder I'm going to write here. Okay. And now you see in the start, Okay, let's not look at these numbers. These numbers are very large. Okay, let's look at the remainder. Remainder 1, 8, 64, 50, 15, 43, 36, 57, 71, 29, 1. Okay, so if I plot it, you'll see after every 10 numbers, I again repeat the pattern. So if you look at this, the whole pattern is same. The same pattern repeating up after every, in this particular case, R is equal to 10. The repetition after which the repetition after which your pattern exactly repeats again. What I'm plotting, I'm on the y-axis, I'm plotting remainder. On the x-axis, I'm plotting my iteration number or R. Okay. So how is this going to help us? Well, it turns out that here we are writing g raised power R. And g raised power R can be written as something like this when my remainder is 1. Remember modulo function. This is n, this is q, and this is r. This is my remainder. Let's connect it with that. So r is making confusion. I should have chosen something else, but here r means repetition. Okay, so whenever I have, after every 10, whenever I have one remainder, I can write that g raised power r as this. Everybody agree with that? Anybody have any disagreement with that? No? Okay. Okay, let's move forward. So now g raised power 8, 8 raised power 10 was this 10737418824. And it can be written as this. This is my quotient, this is n, and this is r. Remember, after every 10, I'm getting r remainder. Okay, and modular side type, actually, this is not right. But anyway, just forget that. So let's work with this way. So if I take 1 on the other side, I get n times m gr minus 1. And this thing I can factorize as gr by 2 minus 1, gr by 2 plus 1. Everybody agree with that? Okay, so now this is something very interesting that I wanted to factorize n, but turns out that there is a number m which when multiplied by n will give me two factors. Okay, and these factors I already know because g I chose myself and r I picked from the graph. In fact, in quantum mechanics, we just do quantum Fourier transform and we get r. But I'm talking about classical. I'm not doing any quantum mechanics here. I'm just simple mathematics. Okay. So now let's see if we can factorize these somehow. So by the way, now if I plug in the numbers, I get this number and I get that number. But remember, m times n was p times q. But now these two factors must be p multiplied by something and q multiplied by something. Okay, so if I GCD this, which number? This number or this number. I can get one factor out of that. Everybody agree with that? The mathematics experts, sir. Okay, so now we want to do this. If we can now, if so we have done most of the algorithm. I have found R. From R, I got one factor, and that one factor I'm going to do its GCD. Okay, so now let's go back to Wikipedia and see how GCD works. So GCD, there are several algorithms. Computationally, a popular one is Euclid's algorithm. Okay, I'm going to give you a quick rundown of Euclid's algorithm. This is the number I want to factorize, and this is n. So this divided by n. What I'm doing here. So this divided by n are now gone here. Okay, so I get 425 remainder 44. Okay, in the next iteration, I take this denominator term in the numerator and the remainder in the denominator. And then I get again something. And I keep on doing it until I get a remainder of 0. And when I get the remainder of 0, whatever is in the denominator, that is my factor. So from Euclid's algorithm, if I apply on this, I get this. And this is no quantum mechanics. This is simply, I went on Wikipedia, and from Wikipedia, I saw that there are several algorithms to do GCD. One of them is Euclid's algorithm. Okay, so once I have this one factor, I can find the other factor simply by 77 divided by 11, or I can again GCD the other one. So first I did this, now I'm going to do this. So if I do GCD this, I will end up getting 7. So now I have both numbers, 7 and 11. These were my two factors. Okay, so just a summary. First step, I guess a number g which is less than n. Second, I calculate g raised per r divided by n and take its and I keep doing it until I start with a remainder of 1, and then again at some point I get again a remainder of 1. So I find the period r, that after r period it repeats, the whole remainder part repeats. It have a pattern to it. And then from there I get these two factors, g r plus r by 2 plus 1 and g r by 2 minus 1. And I then do using Euclid's algorithm or whichever algorithm you want to choose. I just find GCD. Very simple. Okay. Turns out for smaller numbers this is very simple. But finding this period r, this part, this period r is mathematically very difficult. Actually, it's a hard problem. I'm not sure if it's NP hard or not. Somebody could correct me. But this is a very difficult problem. And that's why normal factorizing algorithms we use today on our computers, we don't use this algorithm. However, when Shor in his paper, he introduced that this part, this second step, the step of finding period, can be sped up using a quantum computer. And he introduced that algorithm, which we now call Shor algorithm. Okay, so this is the whole from step 1 to step 4. I did some cheating. Instead of teaching you quantum mechanics, I taught you classical part. But on quantum mechanics side, what we do, we start with a superposition state. So we start with some qubits. I'm going to show you formula how many qubits we're going to start with. And then from those qubits, I apply Hadamard gate to bring them in a superposition state, because I want to find all the factors, all possible possibilities parallel. This is where quantum mechanics speeding up part comes in. And then I apply a quantum gate g raised per r mod n, or a raised per x mod n. This is a gate. And I'm not going to go into the detail of how this gate is formed, but there are again a lot of published work how this gate is formed. And then I apply that gate, and at the output of that gate, I apply inverse Fourier transform, inverse quantum Fourier transform, because we're talking about qubits here. And at the result of this inverse quantum Fourier transform, I get period, because Fourier transform tells you repetitions. Okay, and rest of the algorithm is classical. So this is a hybrid algorithm. This is not a quantum mechanical full quantum mechanical algorithm. First part and last two parts are classical, and the second part of that, or second step, is quantum mechanical. So this is the circuit. We start with two set of qubits, and this is not just one qubit. These are m qubits and these are n qubits. Okay, and how do you get these numbers? You get from here. So m is basically 2 times n, and n small n is basically log to the base 2 capital N. Okay, this you can easily find. And then these qubits on which we are applying Hadamard gate, in fact, Hadamard gate is the Fourier transform. quantum Fourier transform of single qubit. And Hadamard gate is also inverse quantum Fourier transform of single qubit also. Do you know that? How many of you knew it beforehand? That for a single qubit, a Hadamard gate is quantum Fourier transform and inverse quantum Fourier. Why? Okay. Dr. Madiha the other day showed you start with 0 ket, you apply Hadamard gate, you get plus ket. Now this is the Fourier transform part. And now you again apply Hadamard gate, you end up getting a 0. So this is inverse Fourier transform. Same with 1. You have 1 ket, you apply Hadamard gate, you get minus ket. And then you again apply Hadamard gate, you end up with 1 ket. So Fourier transform, inverse Fourier transform. So for single qubit, Hadamard gate has a very unique property that it is a Fourier transform as well as inverse Fourier transform. However, for multi-qubits, inverse quantum Fourier transform is have a different form, has a complete bigger circle. So fortunately for me or for us, there is a function which exists in Qiskit which is called quantum Fourier transform. You just tell it how many qubits you want to make this quantum Fourier transform, and it makes. And you just tell it if it's a forward quantum Fourier transform or inverse quantum Fourier transform. In this case, this is the inverse quantum Fourier transform. Okay, and then you just do measurements. The qubits for which we do not do Fourier or inverse Fourier transform, these are called ancilla bits. Okay. Any question? Please ask questions. Ji? This is ancilla qubits. Ancilla qubits. The qubits which never became part of the process. They were just straightaway observers, right, sir? Or maybe my definition relatively correct. Okay, so back in like 2016, 17, when I started working on Qiskit, so Shor algorithm was part of Qiskit. So this is code from that time. So we are frozen in time. And then today I have made a function using quantum Fourier transform, and basically it's a phase estimation. Okay, can anybody tell me why Qiskit removed Shor algorithm from their library? Anybody? Sir? Because number one, the algorithm which was being used was no longer an optimal circuit. Okay, there was a lot of things happening. And then second thing was that all the developers at Qiskit thought that since Shor algorithm is effectively a quantum phase estimation, so it's better to construct a Shor algorithm using quantum phase estimation instead of just giving everybody a just block. This is Shor algorithm. That's it. Okay. So, and there were some other reasons also. There were these two reasons which come to my mind. Okay. So I just import Qiskit here. From Qiskit algorithms, I import Shor, and then the number which I want to factorize, like n equal to 21. And larger numbers, it becomes very slow. I've gone to very large numbers also because I had access to 127 qubit quantum computer, thanks to Major Bilal. Okay, so we ended up going to large numbers, but we were never able to run it at 127 qubits because after I think after 50 or 55 qubits, we would still get out of memory error. Why? Because for the classical part also it needs to run on your computer. So your computer, like my laptop was not strong enough for that. And my HPC, unfortunately, it was off air. It was air gapped. So I could not connect my HPC on internet at that time. So I was never able to run it on a but I did a lot of simulations on Shor algorithm, but I was never able to connect my HPC to IBM system. Anyways, so This is very simple. I define a variable show or an object show which comes from this function, and I just give as an input. I just tell it which backend, like where you want to run. Either you want to run locally or you want to run it on IBM backend, or you want to run it on Kubernetes or Amazon or whichever backend you're working on. I think Dr. Sara and Mariam showed you how to run it on IBM backend, right? Did they show you how to choose a backend? You just run out simulation. Okay. Anyway, so now when I want to factorize, so I would just do show dot factor and I give my number which I want to factorize, and after that I can extract the results from this object I call result. So result dot factors zero. Zero means the first possibility because this is quantum mechanics. So nothing is for sure. Everything is probabilistic. So the zero will have the highest probability, one will have lower than two, and then so it will give more than one answers. And in this case, I'm just picking one of those. So now and the this code I'm going to show you. Okay. So okay. मैं इसको स्क्रीन शेयर कर दूं. Okay. Uh, uh, okay. Is it visible? Okay, so here I'm defining all the things which I'm going to use here, and this is where I define my backend. So in this particular case, I'm okay. So in this particular case, I'm doing local simulation. Okay, and then I go further. Here I define n equal to 21 or whatever, and then I define the shore object. Shore is equal to shore, and then I don't give it the number. I just give it which backend to run on, and then here I get the result. Result is equal to show dot factor, and this is where I put in my number n, and then it factorizes it, and then bunch of printing. So I want so from the printing you can see I want to factorize 21. Number of qubits required is 22, and list of factors as computed by Shor algorithm is 3 and 7, which is correct. And then actual number of qubits in this particular quantum circuit used is 22, and total number of gates used is 23, and these are the different gates which are shared. Okay, and this is the quantum circuit. So you see I'm defining two type of bits, up bits and down bits. Down bits are my ancilla bits. Down bits I do not do superposition, up bits I do superposition, and there is just one bit which is down 0. I just apply a NOT gate on it, so all of the other bits are at 0, and down bit 0 is 1 cat or cat 1. Okay, and this is the gate 2 raised by x mod 21. Okay, and then this is the inverse quantum Fourier transform, and these are the measurements. And reminded, I do measurements only on the up bits, not on the down bits, because down bits are will not play any role here. They are required for this circuit, which is for this gate 2 raised by x mod 21. And then I can again say circuit dot draw dot decompose, so it will give me what's inside this gate, and this is like lot of gates, 23 gates total. Okay, so there's a big circuit which I combined together into a single block.
So when you are talking about the up bits or down bits, so you means that the molecule or the particle should move clockwise or anti-clockwise?
No, it have no association with that. Just up and down.
Just up and down.
Yeah, it have no physical significance here. Okay. So, can you go back to my slideshow? I shared my presentation over there. This one, the number 2. F5. You can just click here. Okay. Okay, so this was the difficult part. Now this is the fun part. Okay. So now this table I created. Like I just gave a rundown from 2001 until 2026 until now. All of the attempts to factorize the numbers. Like 15 was factorized in 2001. 21 was factorized in 2012 using 5 qubits. And I also gave the which algorithm is being used. So you can see in the start, Shor algorithm was being used, and then this one was compiled. This one was on this one was on NMR quantum computer. This one on photonic quantum computer. This one on ion. Yeah, what happened?
They are not able to.
Okay, thank you. Okay, so we keep on moving forward, and then you start seeing adiabatic. These are quantum annealing systems or similar to quantum annealing systems. And then quantum annealing system, you see this is a big number. And then we started doing QA, and Schnorr algorithm. You know why now you start seeing Shor algorithm no longer being used in the front line of research, because Shor algorithm is no longer used these days. Shor algorithm is only for teaching. So instead of Shor algorithm, there are other new algorithms like QA and Schnorr hybrid algorithm, which is down here. And up till 2022, this was the biggest number that was ever factorized. However, in 2025, this one, this is a very big number, 2 raised by 2048. I'm going to show you in details. Okay, for the previous ones, you can see these are all the papers. This is just rundown of all. I just summarized all the research from 2001 up to 2026 for factorization attack. But now I'm going to focus on this paper. This paper is really very interesting. Okay, so the title of this paper was given to me by Major Bilal. You remember this paper? He was my student at that time in NUST. So this was the first successful factorization of RSA 2048 integer by D-wave quantum annealing computer. By the way, we are doing Pakistan is banned on quantum D-waves quantum annealing systems, and I can give a full talk on how D-wave work, and maybe a whole week workshop I can do on D-wave, because it's very different than what you have learned today. uh, what what happens on D-Wave, you start with a Hamiltonian, and we work with time variant Hamiltonian. So we start with an initial Hamiltonian, and then we evolve it over time to the final Hamiltonian, which is close to our answer. Okay, so it's a very different sort of thing. So I won't be able to teach you on that. Maybe show you something, but not teach. Anyway, Brigadier Razak and me, we have been working on, since we do not have access to D-Wave, none of Pakistan or China or Russia or Middle East, none of these countries have access. Outside America, Europe, there are only 3 countries which have access. Which 3 countries? Israel, India, Japan. Okay, So we have tried to get access through various means, various, legal or illegal means, but we haven't been very successful with that. Okay, so what we have done is we are setting up a D-Wave simulation of D-Wave system on a high performance computer in Pias. We're working on it, and maybe a couple of months you will hear that we have one facility where you can run not on an actual D-Wave computer, but on a simulation of that. But simulation will involve all the programming and everything exactly same, because we will be using D-Wave programming API. So the idea is that we want to get our students at PIAS and NUST familiarize with how to do quantum computing on a quantum engineering system. Anyways, this was the number. You can see how large it is from that paper. And then this is P and this is Q. Imagine how huge numbers these are. Okay, not possible on a calculator.
So these are in 2 raised to power format, or just these are the complete decimal number?
This is complete number.
Decimal.
This number was 2 raised per 2048. This n was 2 raised per 2048. Okay, so this is one number. So in that paper, they factorize 11 numbers. This is the second number. Like previous one was first, and this is second, and this is third. Okay, and then more, and that's it. So in this paper, they have been able to demonstrate like 11 numbers, 10 to 11 numbers they were able to factorize. However, the mainstream community after that paper, there've been a lot of intense discussion on that paper, and you can read about that discussion if you go to internet, and especially if you go to that publication. A lot of mainstream physicists or quantum physicists believe that they picked those numbers such that those numbers were easy to factorize. So this is not a general demonstration of quantum annealing capability, because since we are working on quantum annealing for a couple of months now, like formatting a problem into which is called cubo problem. So formulating a cubo problem from the number is the actual task. It's very difficult. Okay, there's a lot of you need to come up with an algorithm. Okay, in this paper they discuss that algorithm also, by the way. So that is difficult. So that's one difficulty. But anyway, this is state of the art. So now I move to the other presentation. Can you? Number 3. Number 3. Yeah, learning with errors.
So we
Okay, so now what I'm going to summarize first what we have talked today in the first 3 lectures. So, like the take-home message, not the summary, but the take-home message. So the first thing is that RSA is based on the security of RSA is based on prime factorization, while the security of ECC and Diffie-Hellman is based on discrete log problem. You guys did not ask me a lot of questions, so I was able to smoothly sail away from those difficult things. Please ask questions. I'm saying this now because this is my work. I've been working on it since 2021 or 22. So I can handle questions. Okay. Anyway, so Shor algorithm can factorize RSA. I think I don't need to prove it to you. I already, you guys are, how many of you are not convinced that Shor algorithm can break RSA? Okay. So I think I've been doing a good job, or you guys just don't want to raise hands. Anyway, and for ECC, as I told you that ECC and Diffie-Hellman, for them, Shor algorithm can be modified into a discrete log problem. Shor's version of discrete log problem. On the same side, on the other hand, an optimization algorithm which is called QUBO, a quantum unconstrained binary optimization, or in general it is called BQM. Okay, exists on a quantum annealing system. Why quantum annealing? Because quantum annealing computer, which is not a general quantum computer, right now D-Wave Advantage has 7,660 qubits on it. This number is huge. Okay, they don't have those qubits available fully. Like they have like 5,000 qubits at this moment in a functional state, but 5,000 qubit also is a huge number. So I can you've already seen from the previous paper that large numbers and can be easily factorized if we can like formulate a problem which instead of doing quantum phase estimation like we do in Shor algorithm, we can do optimization problem, which is called QO. I'm not going to cover it today. Uh, I teach that also, but today I'm not because lack of time. But anyway, so this means that somewhere out there, somewhere like wild, and if you're unlucky enough to find to randomly generate a number n which is easy to factorize, then somewhere somebody is sitting who can guess, who can generate private key from your public key, and this means we are compromised. What is compromised? Our entire banking system, HTTPS, messaging applications, dark web, cryptocurrency. Maybe I can give again full day talk, a series of talks on why cryptocurrency cannot be broken. But anyway, there are post quantum versions of what you say, post quantum versions of cryptocurrencies also exist, like Aerial Coin, Tide Coin, Quantum RL. These are some cryptocurrencies which are quantum secure, which are believed to be quantum secure. So there is one thing which we call quantum doomsday or Q day. Quantum doomsday is a day when somebody somewhere in the world will have the capability to get your private key from your public key. Okay, and on that day, everything will be compromised. First of all, first thing which is going to break down is going to be your banks. Okay, you use like online apps to access your bank, but banks use a very different system which is called Swift. In Pakistan, the system is called Swift, and in US, it's called Automatic Clearing House (ACH). That system makes sure that money gets transferred from one bank to the other. Okay, and that system is going to break down if somebody has the capability, which I've already shown you that people have already published that they could factorize numbers. Okay, so these are from different news items. Somebody says it's quantum doomsday is here. Somebody says quantum doomsday is like 30 years far in the future. Somebody says within next 5 years it's going to happen and all that. And then there is this thing which is called harvest now, decrypt later approach. Harvest now, decrypt later is that the big intelligence agencies internationally, like NSA, like GCHQ, which is UK's intelligence agency, or FSB, which is Russian, what they're doing, they are collecting all the top secret encrypted data from all over the world, from over the internet. Okay, and they're saving it now because in the future when their quantum computer will be capable enough to break RSA encryption or ECC encryption or Diffie-Hellman encryption, they're going to decrypt those documents then. So imagine now our Pakistan investor to US sends a very top secret cipher to pawn off this, or Pakistani prime minister or our general, okay, or our military attache send a top secret message to our journal and it's going to be deciphered in next 5 years. What kind of existential threat we have on ourselves? Okay, so that's something which is very serious. That's why almost all the governments internationally, they're rushing towards coming up with quantum resistant asymmetric algorithms, because I already told block ciphers or stream ciphers or symmetric ciphers, they are to some extent quantum resistant, but asymmetric ciphers are not. Unfortunately, when you do long distance communication, you're dealing with asymmetric ciphers. Okay, and that's where the problem is. So how to get rid of, how to circumvent? This is another paper in which they have shown that RSA and ECC, they have compared that how easy it is to break RSA and how easy it is to break ECC, and estimated classical time and time on a quantum computer. Okay, so these are very scary numbers. So to mitigate this, National Institute of Standards and Technology, which is the US of government department, which standardizes algorithms and which recommends rest of the government entities within US to, which algorithm to use to store secret and top secret documents. So they ran a competition which started in 2020 or 2019. So do you remember the date? Actually, at that time it was not decided that Kyber is going to be. When we started our research, I started my research at Nilope using this algorithm. At that time, Kyber was one of the candidates, but it was not decided that Kyber is going to be. But we were just lucky that we were working on Kyber, and Kyber ended up becoming a standard. Anyway, so Kyber, they, in November 2022, they decided Kyber is going to be the standard for public key encryption and key encapsulation mechanism, and dilithium, Falcon, and Sphinx is going to be the standard for GSA. What's the meaning of Kyber or dilithium? How many have watched Star Wars? Star Wars? No? Well, my generation used to be big fans of Star Wars. Okay, so in Star Wars, there is a weapon used, lightsaber. So lightsaber have crystals. There are different names of those crystals which power the lightsaber. So one of the crystal was named dilithium, another crystal was named Kyber. So the name convention came from over there. Okay, and then in August 2024, they finalized Kyber into MLChem and published a document FIPS 203, which is right now the standard. And then dilithium was standardized for digital signature algorithm, which is under FIPS 204 document.
Either they use traditional languages or they have developed some their own languages, so that if we can just read their.
No, this is if you look at these documents, if you look at any of the algorithm documents, cryptography algorithm document on NIST, they are in pseudocode. So this means you can deploy it on any language. You can deploy it on C, you can deploy it on Python, you can deploy it Rust, whichever. That's not a problem. Now with ChatGPT and DeepSeek and Claude and all those AIs, translating one language into another is not that of a big problem. Once you translate it, auditing that code is a problem. You see, you need to audit it that this translated code is according to this document. So they gave those documents, and you can audit the code according to those documents. So,
Mathematics and latex.
mathematics have no language. Okay, mathematics is universal, right? Okay, so now what Kyber is or what dilithium is called learning with errors. But before teaching, explaining what learning with errors is, I'm going to explain what learning without error is. Learning without error is easy to understand, and then I move to learning with errors. Okay, so so far what we have been doing, like private keys and public keys are usually just bytes, okay, just numbers, and we use model arithmetic to generate those numbers. Okay, but now what if instead of those numbers, because now computers are very fast, what if instead of those numbers, our public keys and private keys are equations, mathematical linear equations? Okay, so I propose one way of doing that. Like this is my public key. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 equations with 4 variables. Okay, and then their solution is the private key. Okay, this is the solution and I can solve it. But the problem is the solution is trivial because I have 4 variables, 10 equations. I just need 4 equations to calculate those variables. Okay, so that's not a big problem. So this was I just picked 4 equations from there, convert them into matrix form, and then take inverse of this, bring it here, and I just have to find inverse of that, and I can find the private key. And this was my private key. Okay, so this is trivial. So this means the solution is trivial for a classical computer, and hence private key can be guessed from a public key. Now, this situation, how can we make it non-trivial? Sorry? Then again it is going to be trivial.
So by changing mathematical operations?
Yeah, good idea. So what I'm going to do, I'm going to add errors into it. Single digit errors, either plus or minus. Okay, so by doing so, what I'm doing, I'm converting these equalities into inequalities. And now this equation is unsolvable. From this, I cannot calculate x, y, z, and w. Very difficult. You guys agree with me on that? Now you cannot solve these equations, okay? Because these are not equalities, these are inequalities. So infinite number of values exist for x, y, z, and w, right? But somebody who have the private key can have the exact numbers, right? So now this is becoming a hard problem. Not an impossible problem though, but a hard problem. I can make it even more harder, that instead of reporting these numbers, I just report their modulo 89. Okay, everybody is comfortable with modular arithmetic, modulo function, right? So now this is my equation. But now this is impossible to solve. And this is called learning with error. Learning with error, why? Because these are the errors. And now I have to do some kind of learning. Okay, so when I started working on learning with errors, I thought maybe there's going to be some kind of, artificial intelligence happening somewhere. There's no artificial intelligence. I'm going to show you the algorithm. Okay, so step 1, I generate a set of equations, and then their answer is my private key. And then instead, I added some single digit errors into on the right hand side, and then I do modulo 89 on the right hand side. Okay, and on the public channel, I just send these equations to POP, which is my public key. Okay, now eavesdropper cannot guess the private key. So now, why modulo 89? Remember this figure. This is 0, and then this whole, after rotating, it comes to be 89. Again 0. So the other side is 44. This is very important. Okay, these are some of the modular examples, right? Everybody's comfortable with that. So now what we do at the encryption step, Bob will pick 3 of these out of these 10 equations, any 3 random equations, randomly he will pick from the public key. So public key have 10 equations, we just pick 3 equations out of that. And just for your memory, I've broken them into the errors also, because in the actual situation, errors will not be there. This is error will not be shown. You will just get like 39 here, and then 20, and then 49.
So that means that when your data is staying, either it is in the storage format or it is transferring. So you are deliberately just putting that thing to confuse the thing.
Yes, I've done this to confuse Eve. Okay, so now I add the Bob will add, so Alice have transcend those 10 equations to Bob. Okay, very easy, just WhatsApp, right?
By any medium,
By
not
any
the
medium.
secured medium, by any medium.
By any medium. So transmitting equation these days is not a big deal. Okay, so now we have done it. So Bob has picked 3 equations and he added them together. So this is the final equation, which is the sum of all these. Remember, all these numbers are in modulo 89. I just wrote them here just for you to remember. And then if Bob wants to send a bit 0, he will not do anything. He will just send this equation. So this is this, and here 20 minus 1 is 19. So he will just send that. Okay. And then if he wants to send 1, he will send add 44 into it. Why 44? 0. The other side is 44. Okay. So now what Bob have sent to Alice for 1 bit is 1 equation. So if just a small sentence, you can imagine how many equations Bob will be transmitting. A huge number of equations. But today's modern high-speed internet, this is possible. Okay, so now Alice received that equation, which is this. In this particular case, what Bob have done, he wanted to send 1, so he added 44 into it. Okay, so we got this. But remember, this is 63 is 44 plus 19. Okay, just for you to remember. Alice doesn't know this. Okay, this is just for you to remember. But Alice, what Alice have, she have the private key. So she will solve the left hand side of the equation. And when she solves the left hand side of the equation, she gets this 8564. And then 8564, she do mod 89, she will get 20. Okay, and now this 20 we subtract from this 63. So 63 minus 20, you get 43. If this is close to 44, you have 1. If this is close to 0, you have 0. Let's try at 0. Let's say Bob sent 0 bit. So you would get this. 2. So Bob would have sent this 79 plus 2. Okay. This 2 came from the error part because we added error. Okay, so now again Alice will plug in the private key, will solve it. We get 8000. 8000 mod 89 is 79. 81 minus 79 get 2. 2 is closer to 0. This means that Bob has sent 0. And this works all the time. And people have checked it. It works quite like a charm. Okay, and this is basically learning with errors. But this is very inefficient. I'm going to make it more efficient for internet, okay, for communication. So this technique, which is called learning with errors, is being used in lot of different cryptographic algorithms, which are Kyber, dilithium, NTRU, NTRU prime, PQ, NTRU sign, Bliss, Dinky, Prodocam, New Hope, Falcon, Saber, 3 bears, round 5. These are some of the algorithms in which this idea is used in different ways. So NIST decided that Crystal Kyber is good for secret and top secret, but for top secret, they recommended that Kyber 1024 be used, which is NIST security level 5, and Kyber 512 is NIST security level 1. 768 is NIST security level 3. So for top secret communication or top secret data, NIST security level 5 is recommended, which is Kyber 1024. Okay, and this is quantum resistant. Okay. So now, so why is this quantum resistant? Nobody asked me this question. Because instead of factorization problem or discrete log problem, we placed here another type of problem, which is learning with errors. Okay.
Because of that, quantum cannot guess
Okay.
the
So now,
operations.
yeah. So now the previous example which I showed you about learning with, this was just for learning. This is this classroom level thing. Actual situation is as follows, that if I have three matrices. A is a square matrix, S is a vector matrix, T is a vector matrix, vector or column matrix. Okay, so if A times S equal to T, then this is an easy problem, and this problem is called learning with error, learning without errors. But if I add A times S plus E, E is a vector which is errors. Okay, then this is a hard problem. This problem is not solvable. Okay, so now what we do, we keep A and T as private key, public key, and S as public key. Okay, and remember the analogy from the previous example. This was the solution, S was the solution in the matrix form. So this is basically same problem presented in a different form. But there is one very important thing to remember here. The thing to remember is that each of the elements, like for Kyber 1024, this is a 4 by 4 matrix and a 1 by 4 matrix. Okay, so each of the matrix element is not a number but an equation of polynomial order 256. And not just that, because of a certain reason, that polynomial is ring polynomial, which Brigadier Razak the other day in his presentation tried to explain to you what a field is and what a ring is. Okay, this is a very particular type of polynomial which have very particular properties in pure mathematics. So all the quantum mechanics I wanted to teach you was like in lecture 1, 2, and 3. Now what I'm talking about, I'm talking quantum resistant algorithm. There is no quantum mechanics in there. Okay, this is a different type of mathematical problem which a quantum computer cannot crack. Okay, so from mathematics point of view, the A matrix defines the n-dimensional matrix. So these are different lattices on that lattice. So A defines a lattice. This is a way to visualize it. And then these T and S are vectors in that matrix. So this is T and this is S somewhere. Okay, anyway, these are so different vector matrices or column matrices are basically vectors on that lattice. This is why it's called lattice cryptography. Okay, so now how the algorithm works. In the start, we take 32 random bytes as an input and pass those 32 random bytes to SHA-3512. Everybody familiar with SHA-3512? That's why I was spending time in the first lecture. I spent quite a bit of time on things. Okay, and these 32 random bytes can come from a pseudo-random number generator or cryptographically secure pseudo-random number generator, which is currently being used, or in our case, true random number generator or quantum random number generator. Okay, and then out of so SHA-3512 will return 64 bytes as an output. Okay, and out of those 64 bytes, first 32 bytes will call them raw, and last 32 bytes we call them sigma. And then there is an algorithm. I'm not going to go into details of that algorithm, but it's not a very complicated algorithm. But there is an algorithm which from these from row it generates matrix A, and for one particular value of row, every time you get a particular that same matrix A. Okay, it cannot be changed. And then from sigma we generate S and E matrices. So just trust on me that we can do that. Okay, just simple for loops. In case of A, there are 2 for loops, and then just a thorough use of hash function. In that particular case, we're using shake 128 and shake 256. Okay, since I did not go into the details of shake 1 2 8 2 5 6, that's why I'm not going to. And similarly, for generating from sigma to generate S and E, again, just one for loop and just good use of hash functions. Okay, now T is calculated by multiplying A with S and then adding E into it. However, the problem is adding to column matrix is not that of a difficult thing, but multiplying a square matrix into a column with each element being a polynomial of 256 order is a computationally difficult part. Okay, so while making these equations, we use one trick from pure mathematics. That trick was that each element of each polynomial is basically a ring polynomial. If it is a ring polynomial, then there exists a unique type of transform which is called number theoretic transform. Number theoretic transform, and this transform can be used to simplify the calculation. Why? If I want to multiply two square matrices F and G, okay, so what I can do number theoretic transform of these matrices and then do an element by element multiplication. This sign is called element by element multiplication. Okay, and then once the final matrix I got, if I take its inverse Fourier transform, then I end up becoming in such that like I have multiplied F and G. So why we each of the element of this matrix is a ring polynomial? Because we want to use at this stage, we want to use number theoretic transform and inverse number theoretic transform to speed up our matrix multiplication. Okay, you can implement the same algorithm without doing that, but that algorithm will be very slow. So this is just to speed up. And by the way, in number theoretic transform, I've I'm not discussing about gentleman, Sunday, butterfly, Cooley, Tucky, butterfly, Montgomery, and Barrett reductions. I'm not discussing those. But in advanced classes, we do discuss those. Brigadier Razak teach this course in NUST, a full semester course. Do you discuss these things over there? Or even then we skip? You discuss?
Hardly something that is meant to
Yeah, but I'm an engineer. Engineers, we don't. I used to be very good in mathematics back in FSC, but then engineering university destroyed my mathematical skills. So then I ended up in PIAS, and in PIAS, my teachers, they worked very hard on me in nuclear engineering to bring that mathematician in me back again. So because of that, when I went to US during the first semester, I got an A in graduate level mathematics. The Alfken and Weber book, this big, thick book. Anyway, but then I met Brigadier Razak. He was head of department of mathematics at MCS NUST. So he's been my teacher in mathematics. Okay, so because in engineering we totally skip pure mathematics, so I had no idea what pure mathematics is. Even during my PhD, we did not touch pure mathematics a lot. Okay. So, but now thanks to him, I've done all those rigorous calculations, and right now I have all these in the coded code form in Python, uh, and I know what these things are, but let's not discuss this here. So now the public key is T and A, but A is because it's like 4 by 4 matrix and each element is a polynomial of 256 order. So it's very difficult to transmit over it. So, but since there is an algorithm which generates A from row. So if I just transmit row, then on the other side also I can generate A. So that's why here save space to make our public key small. We use T and row as public key, not T and A. This is like a practicality thing. And then private key is S. Okay, so how do we send a message now? So suppose I want to send an A So A in ASCII is hex code is 41. So in bits is this. So I just each of the bit is, power of is coefficient of these polynomial. Okay, and now I can send any number from 0 to 256 bits. Okay, so all the ASCII codes I can send. Do you understand why we are using 256 order of polynomial? So now this means that if I want to send A, so my message will be x raised per 6 plus 1. Okay, and this is trivial. If somebody can understand, please raise your hand and I can explain. Okay, so if you want to send C has hex code of 43, then this is 01000011, then our message will be x raised per 6 plus x plus 1. Okay, so now instead of sending bytes, we are sending equations. So on the encryption side, what we do, we again, so this was the keygen. This part was keygen, so we generated public key and private key. And here we encoded message in the form of polynomials. And then for encryption part, I introduce 4 more vectors, column vectors R, E1, E2, and E3. E1, E2, E3 are errors, and R is the matrix, which have a certain property. And remember, our public key is T and A. Okay, so now now I want to create 2 matrices, U and V, which is going to be a ciphertext. Okay, let's see how we create that. So message is M, because we just for one number, one character, I have one equation. But now I have more things. So I again convert my message into a matrix, 4 by 1 or 1 by 4. Okay, and then I multiply my message with a scaling matrix O. It's a scaling number, some big number, like 4-digit number. And then I multiply R by T plus E2 plus O by M. And this multiplication, again, I'm using entity and inverse entity to speed up calculations. But since T is AS plus E, so what I did, I now transform this T into AS plus E like this. And then when you further simplify it, you will see that you have one term is R times A times S plus R times E plus E2 plus M. M is my message. Okay, and I create another matrix which is U, which is R times A plus E1. Okay, so this is ciphertext, and I just convert them into bytes and ciphertext. Yes, you have a question? You need to ask something? Okay. Okay, so now I have U and V, and by the look on your faces, I see that from something very simple, we ended up creating 2 matrices which are very complicated. Okay, now I'm going to show that this particular form of matrix, why it's going to be useful for us.
Sir, previous slide, I have a little question. So you are using the standard TCP/IP protocol to send this value in a
Yes,
standard packet size.
yeah. This is called encoding and decoding.
Encoding.
I can encode a matrix into a byte form, and then from bytes, I can again create a matrix
Sir,
again.
don't you think that your created message is too much big?
Yes.
So you have to sequence them before sending.
Yes, but I have a very big quantum computer sitting on the other side. I have to create something which can beat that quantum computer.
Okay.
RSA was
sequencing
very
will be the no. Sequencing will-
RSA was very easy. Diffie-Hellman was very easy. ECC was very easy. But now I have to fight a quantum computer. Okay. Anyway, so now I have on the on Alice, now Alice received from Bob. What she received? She received UN, and she also have her private key S. Now how we can do? So if we multiply, okay, if I multiply U with S, I will get this equation. Okay, and I can simplify it into R times A times S plus E1 times S. And now if I subtract U times S from V, like V minus U times S, I end up with this very complicated equation of matrices. But now let's start opening brackets. And end of the day, if you keep doing it, end of the day, we reach this point. So here I have my message and then this part, R times E plus E2 minus E1 times S. Okay, it turns out if you look it, if you plot this data, you will see that this is just my message plus some noise. And if I can just filter out that noise, I can have my message retrieved. And this is what actually what we do. Okay, and this is an example. This is I'm using PQ clean, pip install PQC. I've already given you those, examples, uh, those Jupyter notebooks. So here I generate key pair, public key and secret key. And you can see the public key is 1568 bytes and private key is 3168 bytes. They're huge, but not that huge. Okay. And then uh, encap at decap, decapsulation, like you guys remember key encapsulation mechanism. So now everything I taught in the first three lectures, they're somehow being connected in this talk. So I just camalc.encap and I just give it public key and it gives me a key and a cipher key. Key I keep it to myself and cipher key I send others with. Is it okay? And so this is you can see this is my key and this is my cipher key. And on the other side, on the Alice side, I can just decap input cipher key and private key and I get a retrieve key. And you can see this key and this key is same. So now I have same keys on both sides. And on the encryption side, what I can do, I can take 32 bytes from this key and use AES GCM mode to encrypt my message. This is my message hello. And this is now my ciphertext. And this is my nonce. So now I send my ciphertext and nonce to the other side. And here to decrypt it, I just decrypt it and I get my message back, hello. So now this is key encapsulation mechanism, two parts. First part is exchange key on both sides. So on the network, the only thing we are sharing two things, public key, and then we are sharing cipher key. And then once this communication has initiated, both sides have same key, but eavesdropper doesn't have the cipher key. Okay, so because for eavesdropper to have a cipher key, he needs a private key, and private key is absent on communication channel. Now using those keys, I use symmetric algorithm, encryption algorithm to encrypt and decrypt my message and transfer. So this is about it. So in a NILOP and MCS joint venture, we have modified open source implementation of Kyber, and we have heavily modified it to make it more strong. First of all, in PQ Clean and Open Quantum Safe, the algorithms which are being used right now, which have been pushed by US authorities to everybody for free, like OpenSSL, latest version of OpenSSL have post-quantum algorithm, but it is insecure. We have done a lot of research on it, and we found several issues with that. So we have plugged those issues. One issue is that instead of using pseudo random number generator, which make it deterministic, we are using true random number generator. Secondly, instead of using these libraries which may be compromised because these libraries are not developed by us, like SHA-3, Shake, AES, and then AES CT or DLBG. This is one function, a deterministic random bit generator, which is used in standard pushed on us by NIST. So we have replaced those functions which are with our own in-house developed functions. And then we have NILOP. There's another product in NILOP which is called quantum random number generator. So that product we incorporated here, and we tested. We have our own true random number generator source also indigenous using microchips obtained from China. And then quantum random number generator is fully indigenous NILO product, not my product, but one of my colleagues' product. So we have tested those QRNG and TRNG sources on NIST STS, Statistical Test Suite, DieHard, DieHarder, TestU01, ENT, etc. And we believe that the Kyber version we are providing as part of this collaboration at NIST, which is post quantum cryptography project, is the most secure version of Kyber in the world. Furthermore, we have developed more algorithms like Kyber 1280, which is under audit right now, then 1536 and 1792. We have already developed those algorithms. So now they are being audited by cryptography standardization setups. Just a second. This is the first product we developed. This is called Cryptic, quantum cryptography using identified countermeasures. This is a public key encryption. This we developed in 23 when our collaboration started. Now this is the final version, which is one is message encryption. This is Cryptech CEM, comprehensive encryption mechanism. If you see, there is a symmetric cipher part. Cryptech is means quantum encryption, quantum resistant, quantum hardened encryption technology. Cryptech. So this is our asymmetric algorithm, and for symmetric algorithm we are using quadruple cascade: Serpent, Two Fish, Salsa, and Chacha 20, all in a cascade, so that NIST cannot decrypt it, or they're going to have big issue with their supercomputers, and they end up churning their supercomputers for like 20-30 years just to decipher it. And next message will have a different key. So each message have a different key. And then we have a file encryption software which we call comstech-oic, which can encrypt different files, including executable files. And then we have a mobile version. This is very recent work. We have a mobile app also. So thank you. These are my email addresses.
Well, here our 5 days training workshop is including. So it was a wonderful experience. Well, let's wait for Haris for a couple of minutes. as well. There were around 40 people physically available, and then there were around 300 applicants, and per day around 80 to 100 people were present per day. So that was a good score. That's a good thing. So it's the first training workshop at Comstech, and for that reason, this is the first training workshop in OIC countries as well, which is providing the basic concepts and tools and techniques in quantum computing and quantum information. So it was free. It was free for everybody. So that was again a beneficial thing. So many people, I hope, enjoyed, benefited from this, and could now from here onward continue their journey. So that was very nice. Many people has come to us and then asked that there should be a possibility to discuss and get help in future as well from our resource persons. And for that reason, we have made a working group, and that is a WhatsApp group we are making in the form of quantum computing and information. So anybody who wants to join it, very much welcome. So through that WhatsApp group, it will be possible to communicate in future as well. And second thing which I want to convey that we are also launching the first quantum journal as well. So it is ecosquantum.com. So you can visit it even now on the web. It is available. So here we shall be having yearly publications on the latest research topics and in the form of research articles, review articles, and you can find also some news and announcements up there as well. So that would be again a good way to keep ourselves in contact in future. Thank you very much. Allah Hafiz.